Good afternoon. This is the last session for today. This is a tutorial 2 session. I am the session chair. My name is Juan, working for Korea Internet and Security Agency. Today we have an outstanding speaker whose name is Lee Ho-jun. He is a professor at Seongyungan University, working in the Department of Computer Science and Engineering. He received a PhD degree from KAIST and had a bachelor's degree from which university is it? University of Texas, Austin. His research interest area include operating system security, trusted execution environment, program analysis, software security, and secure AI computation in cloud. Please join me in welcoming Professor Lee Ho-jun to the podium. Thank you.
All right, sorry about the little confusion. So we're gonna begin again. So welcome to the tutorial. We're gonna be discussing isolating and protecting sensitive program components with Intel SGX. So I'm gonna start off with a little bit of self-introduction. So my name is Ho-jun Lee, and I'm the leader of the Systems Security Lab at Seongyungan University. So our research areas include systems security and trusted computing. So basically, we would like to take a look at the existing systems, find problems, and propose architectural or software changes to fix that. So in more detail, we do a lot of software security, operating system security, and as with today's topic, we also do a lot of confidential computation and hardware designs for trusted computing. So a quick advertisement. So we are hiring. So we are hiring all positions, postdocs, masters, PhD, as well as the undergraduate interns. So if you are interested, don't hesitate to drop me an email. All right, so in this tutorial, we're gonna cover the general concepts of trusted execution environments, as well as the architecture of SGX. And then in the second part of the tutorial, we're gonna be seeing the examples that we prepared, which are in Docker container, Docker image formats that you can download and try yourselves. So using the examples, we're gonna learn SGX development methods and patterns using those examples. So these two examples are secure password manager. About the question mark, we're gonna get to that later. And the second example is confidential deep learning in SGX. So this tutorial is more geared towards the beginners, people who are not necessarily experts in system security and trusted execution environments. So no need to get scared and just follow the examples and learn the common programming patterns in SGX. All right, so we're gonna have a 10-minute break after the first half of the tutorial. The first reason is to save my voice box, of course, but another reason is that it takes a little time to download the Docker containers and then set it up. So please use that time to do that for the second part of our tutorial. All right, I'm gonna start with a brief introduction to trusted execution environments. So we all use software, right? We use software every day. The problem with today's software is that they are huge. In case of Google Chrome browser, there are over 6.7 million lines of code. This data was taken a few years back, so that means the code size probably has grown. So it should be, my guess is it should be around 10 million at least. So in case of Android operating system, it is even bigger at 12 to 15 million lines of code. And OS kernels are also large. In case of the Darwin kernel for Mac OS is 86 million lines of code. The Linux kernel that we all know and love is over 20 million lines of code. The second problem with the software today is that they are complex. So today's software tend to be event-driven, object-oriented, a lot of message passing, a lot of different complex logics. So if you have ever reverse engineered any commodity software, then you'll know that modern software is pretty complex. So today's software is huge and complex, and what can be wrong with that? So it is vulnerable because it's huge and complex. We have experienced a few worldwide zero-day breakouts, such as WannaCry, Heartbleed, and so forth. So software vulnerabilities just nowadays affect everyone around the world. And also, Google Bug Bounty program tells you about the value of those zero-day vulnerabilities. So Google does this every year, and last year, Google awarded a total of $6.7 million for the vulnerabilities found on their products. So that value, 6.7 million, talks about the value and importance of finding vulnerabilities and fixing them. So we have experienced the problem of software security over the past a few decades. So it's a decades-long problem. So we have all kinds of different runtime mitigations, compiler-based mitigation, runtime mitigation, but still the problem persists. All right, so the challenge we're facing today is, again, modern software is large and complex, and it is also constantly changing. There are existing techniques to solve this problem. Secure coding is the first one, right? You have to write secure software to begin with to not have serious vulnerabilities in your program. You can also run static analysis to find and mitigate software bugs. And as a runtime bug discovery technique, there's fuzzing and etc. So they prove to be very effective software bug prevention / detection techniques. But the problem we're now facing today is that we have so many important data, so many important secrets in play. So no method can guarantee the absence of bugs in commodity software. All right, so it's about time that we accept the truth. Realistically, zero bug software is not achievable. It's not going to happen. So we are all programmers here, right? So we know this better than anyone else. You write a program, you double check, triple check, but there's always going to be some kind of bug. And the more complex your program gets, the more likely that there's going to be bugs. All right, so this is this quote basically sums up the trusted execution approach. So it's said by me. So the less you trust, the more secure you become. So trusted execution approach is to not trust everything but a very small subset of your program. So we regard all software untrusted, all unverified software untrusted. And then we create what we call an enclave, where only small, trusted, verified code can be isolated and protected. So TCB is a term we use often in the realm of system security. So we call something that is verified, something that we trust, trusted code base, or TCB. So an enclave can be created architecturally, meaning you modify the hardware to provide such capabilities, or you can also leverage software to create such enclaves. So in the past, a lot of researchers have used hypervisors as trusted execution environments. So in academia especially, it's been at least 2 decades since we started using hypervisors as some kind of security tool. And when a field is mature enough, what you're starting to see is the hardware implementations. So researchers propose different methods and techniques in some specialized field then you start seeing hardware doing that. And I think that's one way to understand why we have hardware technologies like Intel SGX or ARM Trust Zone today. So we are already using trusted execution every day. It might not be every day, but you're using it quite often, I'm sure. In case of ARM Trust Zone technology, is already inside your Android-based mobile phones, and services like Samsung Pay or Netflix are already using the Trust Zone technology to secure whatever their program security is. So in case of Netflix, they use TZ to implement DRM. So they don't want you to steal your videos. So they get the stream into the Trust Zone area and then display it right on your screen so that the video stream doesn't appear on the system, so you cannot steal it. And then this is something that's coming up, so this is relatively new. So we're trying to do confidential computing in the cloud. So cloud is eventually someone else's computer, right? So a lot of dinosaur cloud companies are trying to provide a confidential computing service in the cloud. All right, now that we have established a little bit of background on trusted execution, we're gonna move on to the Intel SGX architecture. So Intel SGX was introduced with the Skylake architecture. So Intel introduced a set of hardware changes, a new set of instructions that programmers can use, as well as a SGX SDK that includes a set of libraries and also the tool chain that allows you to build secure applications. So SGX allows applications to isolate sensitive code and data within its address space, meaning the enclave will be run and positioned alongside with your normal program. So it's gonna be in the same address space. And the killer application for SGX, so this is one reason why SGX is getting so much traction, because as you're gonna see, SGX will allow confidential computing in the cloud. Okay, so in CPU we trust is one word that very well describes the SGX security model. So user applications they cannot be trusted for obvious reasons, right? User applications are diverse, complex, managed by third party, and you're basically at the mercy of the developers to not make vulnerable programs. So user applications are obviously not trusted. Well then, how about the OS kernels? Well, if you go look up the CVE numbers on the Linux kernel, every year there's over 100 vulnerabilities every year. So some years you have 200, some years you have 300, and some good years you have around 100 vulnerabilities. So these are not bugs, these are confirmed vulnerabilities. So kernels cannot be trusted. Then what about hypervisor? I said that researchers try to use hypervisor as a trusted execution platform. The hypervisors are a little better because obviously they're smaller than the commodity kernels, but we are still finding hypervisor vulnerabilities every year. And in case of hypervisor, since a single hypervisor instance can manage the entire cloud machine, vulnerability in hypervisor can have huge ramifications. So even though hypervisors have fewer bugs than the kernel, but that doesn't mean the hypervisors are necessarily safer. And hypervisors are eventually, it's also a software written by people, and it's inevitable that we have bugs in the hypervisors. All right, so in SGX, we trust two things. First is the CPU. We simply trust that the SGX architecture included in the Intel CPU are trustworthy. And also, we talked, I explained what a TCB is. And in SGX architecture model, we also trust the TCB that is placed inside the secure enclave. So we trust two things, and we don't trust anything else. So by trusting less, we get minimized attack surface. For example, we don't need to worry about the possible vulnerabilities in the software stack that comes below the user application. All right, so hardware security parameter. So this is the security parameter of SGX in terms of hardware. So the security parameter in hardware in SGX is the CPU package, meaning the unencrypted data or code can only reside inside the CPU package. So whenever the data has to come out back to memory, the Intel CPU will automatically encrypt and then save onto your DRAM devices. So this security parameter effectively defends against, for example, memory snooping attacks. So for example, the attacker can place a probe on the RAM slot to listen to what you're computing on. This defense mechanism effectively mitigates that. So this is a built-in feature to the CPU itself. So it means that if there's any CPU to memory movement, the data will be automatically encrypted. For instance, if there's a page out, then it will be automatically encrypted. And if there's too much pressure on the cache and you have to flush out some of the code and data, those are also automatically encrypted. Okay, so in Enclave, we have what we call EPCs. It's called Enclave Page Cache. So these are basically pages that belong to Enclave and thus protected. So during the boot, SGX or the Intel CPU reserved a range of DRAM so that they can be used for security purposes. And EPC is assigned inside the PRM to provide secure memory for enclaves. And a structure called EPCM stores the state of each memory, each page, and keep track of the correct mappings. So for example, if your operating system, so we said operating systems are not inside the TCB in SGX security model. So EPCM is who verifies if the OS correctly mapped the pages according to the given specification. So for example, one EPC is supposed to be read-only, but your kernel maps it as read and write. EPCM will detect that and automatically abort execution of the enclave. All right, so now we know what EPCs are, and EPCs are mapped into the virtual address space just like any other user space component. So inside your user program, there's untrusted code, which is also your program, and there's a secure enclave zone that stores the enclave code and enclave data. So they're placed within the same address space. It's not like you have user and kernel where you have a different address space. But there's separation of execution modes. So it means that now the user execution mode, for example, in Intel, it will be privilege ring 3. And those, the normal user mode cannot access EPC pages, thus protecting the enclave memory. You have to enter special execution mode that were added in the SGX supporting CPUs called enclave mode to be able to access the EPC pages. So this is very similar to the user versus kernel distinction we have in our system, right? So you have to enter kernel to be able to access kernel pages and so forth. So no software instruction can access enclave memory. That includes the kernel, hypervisor, and a special mode called SMM, System Management Mode in Intel. And even the BIOS cannot access the enclave memory. So you're protected from all the software stacks that sits below the user space. And again, executing context has to be in enclave mode. You have to explicitly enter enclave mode to be able to access enclave memory. All right, so then how do we actually move into and out of the enclave mode? This is called equals and all calls. So equal is enclave calls and all calls are out calls. Equals are used to enter enclave and all calls are used for enclaves to call a routine that is outside its enclave. So equals and all calls are actually conceptual terms. These are actually implemented with e-enter and e-exit instructions. So e-enter and e-exit instructions, if you have history in systems programming, very similar to syscall and sysexit. It's just another instruction that allows you to move in and out of a privilege layer. And we're going to discuss the programming pattern involving equals and all calls with our demos. And of course, the mode switching between untrusted and trusted using equals and all calls have to happen through a predefined and controlled equal and all call interfaces. So again, equals are used to enter and all calls are used by enclaves to access something that is outside. And also there's something called AEX. We're not gonna go into the details, but this is when the enclave has to exit enclave for certain events, for example, interrupts, traps, and things like that. All right, so if you have taken the operating systems, this is operating system 101. So for a user program to make, for user programs to access any system resources, you have to make a system call, right? So to access memory, file, everything, you have to do a system call. So, but you never actually invoke system call as a programmer. That is because we invoke system calls through the C libraries. So if you call printf, for instance, it's gonna write system calls to write into the console and so forth. And one surprise about the SGX is that you cannot use system calls inside the enclave mode. So to explain a little bit of background on this, there is a very well-cited paper called Iago attacks. So this paper explains all kinds of examples that how our implicit trust in kernel can be exploited in many ways. So the code you see on the right is one example of that. So kernel is intentionally giving you a bad random number, and you use that to perform cryptographic actions, then you fall into the trap of malicious kernel. So this implies that directly interfacing with the kernel can be very dangerous, and it can be a very highly potential attack surface. So in SGX security model, they decided to not allow that. So kernel is not part of TCB, and also there's no direct communication with the kernel. Well then, how do you write programs for SGX if there's no system calls? It's almost impossible, right? So you kind of have to use a detour through the normal user space to be able to call something like printf. So the common pattern is that the developer implements all call wrappers or proxies to call libc functions that invoke system calls. So this way, enclave does not have any potentially dangerous system calls that can undermine the confidentiality of the enclave. So we'll come back to this later with the demo. So again, you cannot call system calls inside enclave, and you have to take a detour out to the untrusted territory to be able to reach the kernel. All right, cryptography. So SGX has secure keys fused into the hardware. So this is not stored in the software. This is actually fused into the hardware. There are two types of keys in SGX. One is called root provisioning key, which is often used for proving that you are SGX. And this is a crucial feature that's going to be used in remote attestation, which is another topic that we're going to discuss today. The second is root seal key. So this is a more common key that you can use. So this key is only known to SGX CPU. So provisioning key is known to Intel, so that Intel can operate as the CA. So if you take a signature from the provisioning key and take it to Intel, Intel will tell you that it is one of our SGX CPUs. But in case of root seal key, it's more general purpose. You can derive keys from RSK, and then you can use it for other purposes. All right, so I don't know if you're convinced, but so assuming you're convinced that SGX is very good idea, and you can use SGX to protect your programming data. So what we want to do is we want to run a super secret program compiled with SGX SDK. So you wrote your program and made it super secure with SGX SDK, but you want to run it in the cloud. But you realize that you run into trust issues. So first of all, how do you know if the cloud actually has SGX? How do you know if cloud is actually running your program on SGX? There's no proof for that, right? And there's no proof that your program is running unmodified. So you don't know the cloud service provider has done something terrible to your program and then run it to steal your secret. And these are exactly the objectives of remote attestation. So first, you get a proof that cloud is actually using SGX, using a genuine SGX hardware, and also get a proof that your program inside SGX is unmodified. So the remote attestation, every SGX SDK installed system has what we call the architectural enclave. So this is more like a service enclave that performs the remote attestation for you. So this architectural enclave will take a measurement of your application enclave, and then sign it, and then they're gonna send it back to you. All right, so instead of going into the detailed cryptography, I'm just gonna give you remote attestation steps in human language. So it starts with asking the cloud, are you really SGX? And you get a proof signed by the architectural enclave, and then you present it to the Intel's CA server. And then Intel will tell you if it's one of their SGX capable CPUs whose keys are issued by Intel themselves. So that's how you know it's real SGX. And secondly, you can, by checking the measurement hash from the architectural enclave, you can make sure that your program is running unmodified. And why is this useful? The cloud, right? So in cloud, everyone's adversary, everyone's enemy around you. So cloud is basically someone else's computer, and you can be attacked by the compromised cloud infrastructure, meaning the kernel, BIOS, SMM, or whatever. The low-level software can be already compromised in the current cloud. And secondly, you can, malicious or curious administrator might be trying to steal your personal information or your intellectual property. You can also run into shady co-tenants that are placed on the same computer as you, and he or she is trying to steal the information from you. So SGX allows your workload in the cloud to be performed confidentially. So it's you, the SGX CPU, and the Intel who are trusting in the, where everyone is untrusted in the cloud. So there are already services being serviced, such as the Azure Confidential Computing. So this is Microsoft's cloud computing service, and they're already providing SGX-based confidential computing service. So you can pay for it to run your SGX application in the cloud. So one use of this will be, for example, if you're trying to perform training of an ML model, machine learning model in the cloud, and the data is from some medical institution. You don't want that to be leaked anywhere, right? Not even from the Microsoft. So in such cases, you want to use your SGX knowledge you learned today, and you write your program with SGX, and then use one of SGX supporting cloud services like this one to perform the confidential computation. So there are a lot of papers published on this topic. One example is occlumency. So occlumency showed that you can perform confidential ML training in the cloud using SGX. So this was published in Mobicom 19. Another contribution made by the author is to split up the workload in batches so it can be feed into SGX. So one architectural limitation of SGX is that the memory is very limited. So you have only 96 megabytes of memory in the current iteration of SGX, the SGX version 1. So the authors found a way to break up the workload and then to enable the ML training using SGX. And also there's a confidential MapReduce in the cloud by Microsoft Research back in 2015. And there's also SGX-based database. So database is sitting in the cloud, and even the cloud administrator cannot see your database. So this is one way to secure your client's database and still use the cloud computing services. Okay, now we're gonna discuss a little bit about the problem side of SGX. So SGX sounds like a systems security researcher's dream, right? But there are problems with using SGX, and researchers are trying their best to solve those problems. So one problem is that, so this problem is not common, not specific to SGX, but the cache side channels that we are facing today are also affecting SGX. So there are multiple papers that proved that the existing cache side channels on the Intel CPUs can also affect SGX. So it's been proven multiple times. So this is a real issue. And another attacks are related to the inherent security model of the SGX. So we're gonna get to that in more detail in the coming slide. All right, so we said kernel is not part of the TCB in SGX security model, right? So SGX does not allocate the memory, does not create the page table mappings themselves, but instead let the kernel do the job and then verify the mappings later. So that's the SGX model that minimizes the size of TCB and minimizes the interfaces that might serve as the attack vector. So the attack goes like the following. So the blue box is where your SGX program is located. So you have a few pages in your program, and then the malicious kernel intentionally unmaps all the mappings that correspond to the EPC pages. So of course the page fault is going to happen, and the kernel can observe which memory is being accessed by looking at the address shown in the page fault report. So if there was page fault on page A, then you know that page A was just accessed by the enclave code, right? Then you wait a little, then you find that D was accessed after A. and so forth. So as a result, attackers can learn a lot of things. For example, the order of execution. So if the attacker has the knowledge of the program inside SGX, you can learn which function is in which page, and consequently, the attacker learns the control flow with the granularity of a page. So you can also learn what is used and what is not used. So for example, this is a pattern you commonly see in complex libraries. You use function pointers to connect whichever function that is currently being used, and you simply just don't use the others. So by looking at which page is used and which page is not, you learn which algorithm is used inside Enclave. You can also observe input plus event response observation. So if there's a packet coming in, page C always responds. Then you can probably learn that page C contains some kind of event handler in the page. Another attack is to use, so this is going more physical. So you can place a probe on the DRAM port, and then you can observe the incoming memory. So we said that SGX's security model has a CPU package parameter, right? So we know that the memory from SGX to DRAM is encrypted. Even though it's encrypted, as you can see on the right, you can learn about the access pattern. So the picture illustrates our experiment using a full system simulation. So the program we used here is Hunspell. So it's a simple dictionary library. So by looking at the position of the hash table being accessed, you can figure out which word was queried to the dictionary. So even though things are encrypted, that doesn't mean you have 100% confidentiality. There are always some information being leaked out to the attacker, and SGX is no exception to that. All right, so another challenge we have is the secure I/O. So kernel is not TCP, so that means we don't trust the device drivers and the I/O path. So in theory, this makes secure I/O impossible without active participation from device. So remember our example on the remote attestation. To be able to verify each other's identity and get a quote on that, and then finally establish a trusted secure connection, both parties have to activate in the process. And right now, not many devices can do that. So we have this secure I/O problems when it comes to using SGX. So the requirements are more specifically secure key storage, certificate, and the CA. You have to have a CA outside, right? They can tell you that this is a genuine certificate. So the bottom line is that device has to actively participate in creating the secure channel. And no commercial grade GPU can do this at this point. And there was a interesting proposal from Microsoft Research who proposed a GPU model that is capable of doing this. So they showed that their proposal can make SGX and GPU secure, establish secure communication channel and perform tasks like ML computation and so forth. So what does that imply about the current state of SGX? No GPU support in SGX. So as soon as you use GPU, your secret is sent out to the unencrypted bus channel, and also it is kept unencrypted inside the GPU memory. But things are a little bit different in case of ARM Trust Zone. So ARM Trust Zone trust a trusted kernel. So they have a small kernel inside the ARM Trust Zone, and it interfaces directly with the protected hardware resources, meaning you can enjoy all the secure device driver services. That's why we have more practical services like Samsung Pay or Netflix DRM. All right, so we finished a little bit early, and I would like to take questions about the material so far. So if you have any questions, don't be scared. Don't hesitate to raise your hand. Anyone? All right, so we're gonna be back in 10 minutes. So we're gonna be back at 4:50. Meanwhile, I want you to git clone our example. So you can take a look at the source code. You can also get a feel of what it's like to use and compile and run SGX programs. So please go ahead and clone our repository. I'll give you some time to write down the URL. Right, everyone good? Got it? All right, so if you have cloned the repository,